Alright, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for the next hour. So here at OneClass, if you're tuning in for the first time, we are kind of in this process of verifying solutions for frequently asked questions in chemistry and the mathematics, both in the secondary level as well as in the university and the college level. So based on those, we basically compiled a bunch of math and chemistry questions that are basically sent in by you folks at home, and I've organized these questions in a series of 10 so that we can answer kind of within this hour we can try to answer 10 questions about chemistry or about math, and that we can hopefully verify the solutions, and I can teach you the concepts behind those solutions as well. So my name is Joey. I'm currently a secondary school educator in Ontario. My teachables are currently chemistry and music. However, I'm planning to get my math teachable very shortly in the summer as well. So without further ado, let's get started on these problems here. So we have our first problem here is draw the major product formed in the following reaction. So classic organic chemistry question here. So what we're going to do is we are going to I have here an epoxide. So epoxide, if you recall, it's kind of an oxygen here, and it's a cyclopropane with the oxygen here. It's not, again, it's not, I didn't draw it really nicely here, but this here is an epoxide, and then I have this kind of ethyl chain here. I'm going to react it with sodium cyanide, and it's going to be an ethanol and water as well as our solvent here. So what would that do to our epoxide here? So what's going to happen is basically two things could happen here. When we look at here, this here is an epoxide. So when we talk about epoxide here, we can talk about, there's two kinds of epoxides here. So there's symmetrical epoxides and there's asymmetrical or unsymmetrical epoxides. And all you have to do is kind of look at these side groups here. So in this case, we have this group here, which is simply just hydrogens, and this group here is the ethyl group, right? So as you can see, if both of these groups don't match, then this is a asymmetrical or unsymmetrical asymmetrical epoxide here. And this is important when we talk about especially ring opening epoxide kind of reactions here. So if we have an asymmetrical kind of epoxide here, basically one of two things could happen. Basically every time if you're reacting it with acid or base conditions here, it's going to open up a ring. So we know that this here is going to be a ring opening reaction. And what it's going to do, but how the mechanism behind this is different if it's for an acid or a base. So looking at this guy here, we have a sodium cyanide here is a very, very strong it's not very strong, but it's a basic condition, right? We know that this here, sodium cyanide here is NaCN. I can add it with H2O, and this would be in equilibrium with, we have just simply the sodium ion here, and we have the HCN here. So this here, and then obviously plus with water here. And HCN here is this is a very, very strong conjugate base here, hydrogen cyanide. So this here, it makes it a basic condition. So basically what we have is a basic condition, right? So I have NaCN, and what it's going to do in general, if I had a basic condition, conditions such as sodium hydroxide, sodium cyanide, for example, it's going to basically attack the least substituted ring. So it's going to open through. It's going to attack this least substituted ring. So how I'm going to illustrate for that for you. Let me just erase these lines here. And how it's going to do that, again, I have this negatively charged cyanide group here. And again, as you know, my lone pairs here are drawing a partial negative charge here, which means these guys here are both partial positive. Now, this is the mystery you have to solve. Is it going to attack the left side or the right side? And we know that in organic chemistry, if it's a basic condition, it's actually going to attack the least substituted member. So in this case, it's this guy here. So this guy here is going to come, attack here, and then break up this oxygen, break up the epoxide here. I'll do some black for you. Just come here, attack this carbon, and it's going to break up this epoxide here. This is SN2 reaction. It's done in one step here. And then all I'm going to be left with is I'm going to be left with an OH or HO hydroxide group on this left-hand side. And then I'm going to have 1, 2. And then, so this here is carbon, this here is carbon, here is carbon 1, this here is 2. And then I have obviously 3 and 4, right? And this here will be my hydroxide this here would be my product for this ring opening here. So let's see here. Oh, I forgot the CN, my bad. So the CN is going to come attack here. It's a nucleophilic SN2 substitution. Sorry, this here is an NC, my bad, because I have the sodium, cyanide attacking here. And then I'm going to get, so it's going to be a CN here, and then it's going to be, there's going to be an O here as well. So this here will be O. So 1, 2, 3, 4. I have 1, 2, 3, 4. So this would be on carbon 2 here. So here's OHO. So 1, 2, 3, 4 here. So the solution here is correct. Again, 1, 2, 3, 4. 1, 2, 3, 4. Again, this is bonded to the cyanide group here, and then carbon 2 is bonded to the hydroxide group here. So you could think of this as this here is carbon 1 because it's being attacked here. This here is carbon 1. Carbon 1. Carbon 2 would be bonded to the hydroxide group here, and then also bonded to the ethyl group here, which is this ethyl. Ethyl is here, and this ethyl is here as well. So this solution here is correct. As you can see, the basic condition is going to attack the least substituted guy, so you're going to get this as your product here. If it was an acidic condition such as HCl, it's actually going to attack this partial positive and the most substituted one, and it's going to bring opening. It's going to do a ring opening from that. In this case, the stereochemistry doesn't matter because I didn't have doesn't show stereochemistry, or it didn't show me if it was sticking up, if it was a wedge or a dashed diagram here. So if it does, though, again, you can if it takes place here, you have inversion here of stereochemistry, right? So that's kind of just a little bit about stereochemistry here. So solution here is correct. Good analysis here because I like how they provide analysis as to the ring opening of epoxides in both acidic and a basic condition here. So solution here is correct. Number 2 is asking us write the net ionic equation for reactions of solutions of sodium hydroxide and magnesium chloride. So I want the net ionic equation for sodium hydroxide and magnesium chloride. So let's write this down. So I have sodium hydroxide, which is NaOH. This is all an aqueous solution. Let me draw this a bit further up here. So NaOH. Actually, I need numbers to balance here. So NaOH, an aqueous solution, plus magnesium chloride is MgCl2, right? MgCl2. I'm going to get, I was basically going to do a double displacement. I'm going to get magnesium hydroxide plus sodium chloride, right? NaCl here. So again, what we're going to do is we want to find the net ionic equation. We got to break these guys up to its ions, right? So I'm going to break them up to its ions. So I'm going to get basically Na plus. So let's see, I have first to balance this equation, obviously. Let me balance this first. So I have 1 sodium here, 1 sodium here. That's good. I have 1 hydroxide. I have 2 hydroxides here. So I'm going to have to put a 2 here. So this would be now 2, and this is now simply balanced, right? So I have two sodiums. I have 2 hydroxides here, 1 magnesium, and 2 chlorines here. So let's break this up into its ions, right? So again, I'm going to have here NaOH. So I have two Na positives, plus I have 2 OH minuses, plus I have 1 magnesium. And magnesium has a charge of 2 plus 2 chlorines here. 2 chlorines here, and they have a charge of -1. And this is I'm going to get here, I have 1 magnesium, so Mg2 plus 2 OH minuses, plus 2 Na pluses, and 2 chlorine minuses here, right? So again, as they have here, you have these two guys here. Oh, magnesium hydroxide is a solid. Sorry, so that is correct actually. So my bad. I forgot to write the phases here. But magnesium hydroxide is a solid because actually it becomes a precipitate here. I don't have the precipitate ones, but one of the rules in grade 11 for solubility is that magnesium, basically a metal with any hydroxide here, becomes a solid here. So if it's a solid here, I can just leave it as MgOH2, right? So this is here simply just MgOH2, and I have Na and Cl, and those are obviously soluble here. So I have these guys here, and I'm going to look at this equation here, and see if things appear twice here, right? So I see sodium appears on 2 sodiums here and 2 sodiums here. I see 2 chlorines here and 2 chlorines here. So therefore, I'm only left with 3 guys here. I'm left with only the net ionic equation would be simply just whatever is left over, right? The net ionic equation would be basically 2 OH minuses plus 2 Mg2 pluses would give me MgOH2. And this here is the correct answer. And again, this here is also the correct answer. Sorry, I don't think there's a 2 here. It's just 1 here, sorry. So this here is a 1. So this here is the correct answer for the Net Ionic equation. So solution here is correct. That's good analysis as well. Okay, number 3. So asking us a certain substance has a heat of vaporization at 50.07 kilojoules per mole. At what Kelvin temperature will the vapor pressure be 6 times higher than it was at 345 Kelvin? So we are doing, so we have here the heat of vaporization. So we can say delta H vaporization equals 50.07 kilojoules per mole. And it says asking us what Kelvin temperature will the vapor pressure be 6 times as much, right? 6 times as much than it was at 345 Kelvin. So basically we have here T1 here, delta temperature 1 is 345 Kelvin, and we're looking for a T2, obviously. T2 here is our unknown here. And you can think of the vapor pressure 6 times. It would be the ratio of P1 and P2 would equal 6, right? So we can think of this as P2 over P1 equals 6, right? And basically when we says equals 6, it means because it's 6 times higher, right? So P2 is 6 times higher than P1, right? When it was first initially, right? So we can say here this ratio here equals 6. Now looking at all this stuff, what kind of equation can we use to relate basically our heat of vaporization with our temperature and our pressure here? In the solution here, it says we're going to use this equation here, the Clausius-Clapeyron equation here. And basically this reaction relates all of these guys together, right? It's going to say that the pressure here is proportional to basically e to the power of the negative delta H, or enthalpy of vaporization, divided by RT, right? So we can also rewrite this as, and let me write this down for you, as ln. And basically, I'm gonna just write down the equation for you here. So it's ln of basically P1 over P2. P1 over P2, I believe, yeah. Or this says here P2 over P1. So let me just write this out for you first. Is a delta H of vaporization divided by R times 1 over T2 minus 1 over T1 here. So in this case, they actually flipped this. So they did P2 and then they did T1 minus T2. In this case, it doesn't really matter which order we do it with. But I'm going to stick with this one because this equation is what I've known before. So if P2 over P1 here is 6, then P1 over P2 is obviously 1 over 6, right? So 1 over 6 here, I have and then I'm going to have my 50.7 kilojoules per mole as my enthalpy of vaporization. R is simply just 8.314. We know that through the ideal gas constant, right? R is 8.314. So that's something you're already familiar with, times 1 over T2, which is what we're looking for, right? We're solving for T2, and then 1 over T1 is 345 Kelvin here, right? So 345 Kelvin. And all we're going to have to do is we're just going to do some algebra here, right? To isolate for T2. So I'm going to find ln of 1 over 6 first. So I'm going to take ln of 1 over 6, and then basically I'm going to divide it by this guy here. So I'm going to take ln of 1/6 first. I'm going to get negative 1.79. Sorry, that's 6.918 equals, what's 50.07 divided by 8.314 would give me a value of 6.02237 times 1 over T2 minus 1 over 345. I'm going to divide both sides by 6.02237, right, to get that to the other side. I'm getting a value of negative 0.2975, which will equal 1 over T2 minus 1 over 345. And then I'm going to add 1 over 345 to both sides here, right? So I'm going to add 1 over 345 to both sides, and I'm going to get negative 0.2946463 would equal 1 over T2 here. And then finally, let me just backtrack here. I think I'm getting a negative answer, which is not good here. So let me just think about what I did here. Let's see, if I have a negative answer here, I'm going to get, oh, yes, that's why. So I forgot to convert joules to this kilojoules to joules here. So that's my fault here. So this here has to be in joules because I remember my R constant is joules per moles times Kelvin. So I'm going to have to actually convert kilojoules into joules. So that's actually my fault. I missed a step here. So 50.07 times 1,000 would give me my kilojoules here. So this is 50, sorry about that, folks. This is 50,700, so this will be joules per mole now. And this will give us our good units here. So that's my fault for not using units here. So 50,070 divided by 8.314. Oh, sorry. Divided by 8.314 would give me a value of, this is now 6,022.372 here. And I'm going to divide that number, 1.798918 divided by the answer here will give us a much smaller number. So this is not right. This here is not right here. I'm going to get negative. This is negative 2.975 2 times 10 to the negative 4. So let me just see. Yeah, T1 is here, right? T1, yeah, T2 minus T1. I'm solving for T2 here. And they had 1 over T1 minus 1 over T2. I did 1 over T2 minus 1 over T1. I think it should be okay now. Add 1 over 345 to both sides. I'm getting a positive value. That's good. Let's give me 2.60103 times 10 to the negative 3. And then I'm going to simply do 1 over that. So T2 equals 1 over whatever this guy is. 2.0103 times 10 to the negative 3. And this will give us our answer. So T2 is going to equal 384.5 Kelvin, or you can say approximately 385 Kelvin. And this is very, very close to this answer here. So this, I think it's probably a rounding issue here when I rounded one of these guys here, but this here is the correct answer. So solution here is correct. Good analysis here. Okay, so that's number 3. Let's look at number 4. Number 4 is asking us at 298 Kelvin, the Henry loss constant for oxygen is that. And then it's asking, it's three parts here. So it's a 3-part question. So I might actually, instead of redoing one of these problems, I might have to, let me just look at the solution for the sake of time to just see to see if their logic is sound here. So let's look at number 4. This is at 298K Henry's law constant for oxygen is 0.00130 molar per ATM. So the air is 21.0% oxygen. So asking us at 298, what is the solubility of oxygen in water as opposed to air? So I want the solubility of oxygen in water exposed to air, exposed to air at 1.00 ATM here. So when we look at A here, as you can see, A here, what they're doing is they're taking their mole fraction of oxygen per air, right? Because I remember here, for oxygen here, I know air here is, I'm solving for air here, right? So air here is only 21.0% oxygen. So I can say, I'm going to do the partial pressures. They're relating this to partial pressure, right? Because I don't have the concentration of air. Obviously, I only have the concentration here of oxygen. So I'm going to relate this to partial pressures, and what we can do is we can solve for the pressures. Is we can relate that to the concentration, right? So we know that PV equals nRT, and N and P are going to be proportional to each other. So if we're in a constant volume, we're going to assume it's being in a constant volume. Therefore, it's going to have the same percentage of pressure here. So it's proportional. So we can say the partial pressures of O2 here, the PO2 here, is that what they're doing, equals basically the mole fraction of oxygen times the pressure of air, right? So the mole fraction here is simply just 21%, so 0.21 multiplied by 1.0, right? We're assuming it's 1.0 ATM here. So this here, or no, that's not an assumption, that's given to us. So this here would equal, it would equal, let's see, 0.21 times 1.00 is simply just 0.21, right? 0.20 partial pressures of O2 here, so that's good. And then, so this is going to be the partial pressures of O2, right? And then finally, what we have here is we can now use the Henry's law. Henry's law's constant here is 0.0130 molar per ATM, right? So if we have M over ATM, what we can do is now solve for the molar solubility, right? So we know the molar solubility here equals K, which is Henry's constant, times the partial pressure of O2 here, right? Or you can say Henry's constant here. So maybe I'll put K subscript H here to make it a bit more noticeable. This is the partial pressures of O2 here. And then the molar solubility equals, now I know it's, let's see, from 0.01, so 0.00130 molars per ATM, times 0.20 ATM here, right? And this would equal the molar solubility. Again, ATMs cancel out, and this here, I'm left with this molarity, and that's going to be the solubility, right? So 0.001030 times 0.21 will give us a value of 2.73 times 10 to the negative 4 molarity here. And this is going to be the molar solubility for air here. Of oxygen in water exposed to air at 1 ATM here. So we could do the exact same thing for B, right? For B here, it's just changing our ATM here. So if I did B here, maybe I'll do some blue. I can do the exact same thing. I can find the partial pressure again, and it's going to be 0.21 of O2 here would equal. Let me just do this as a side here. Is going to be exact same thing, right? So 0.21, because again, it's the same percentage, but multiplying here by a different pressure, right? I have 0.897 in this case. So I'm going to do the exact same thing. I'm going to multiply it by 0.897 to find the partial pressure of O2 here. And this here would get me 0.21 times 0.897 would give me a number of, so the partial pressure here is 0.18837 ATM. So this is the mole fraction here. And then I can relate it to Henry's constant, right? So again, I can find that molar solubility equals the Henry's constant times our partial pressures of oxygen here. So molar solubility obviously equals 0.00130 molarity per ATM multiplied by our partial pressure of O2, right, which is 0.818837 ATM. Again, the ATMs are going to cancel out, so I'm left with just molarity here, right? So 0.00130 times 0.18837 will give us a value of 2.44448 times 10 to the negative 4 molarity here. And as you can see, this solution is also correct, right? 2.45. They rounded it to 2 decimal places. That's totally fine. And then finally for C, let me zoom out here. For C here is if atmospheric pressure suddenly changes from 1.0 to 0.897 at 298, how much oxygen will be released from 4.90 liters of water in an unsealed container? So if we have here, if it changes from, again, 1 ATM to 0.897 ATM at a constant temperature of 298 Kelvin, how much oxygen will be released, right? So it's talking about the C here. So C here is, again, we have here moles of O2 release is simply just these two guys subtracted each other by each other, right? So basically I'm going to have, this is a molarity, so I'm going to convert this into moles first, right? So I want to convert it into moles, and then I can then convert it into molar mass, right? So let's see, I have 4.90 times 10 to the negative 4. So let's see. Yeah, so I'm gonna convert these molar solubilities. So again, this one was at 1 ATM, and the blue one here is at 0.897 ATM. So let me just do this for you. So I know that concentration equals moles over volume, right? So therefore, moles equals C times V, right? And the moles here equals the concentration, which is 2.73 times 10 to the negative 4 molarity times 4.90 times 4.90. Yeah. Because remember, moles here is basically moles over liters, right? Times 4.90 liters. This here will give me our moles, right? Our moles here would get, I would get 2.73 times 10 to the negative 4 times 4.90. I'm going to get here 1.337. Oh, shoot, sorry. 1.3. I'll just round it to 2 decimal places here. So 1.34 times 10 to the negative 3 moles. And this is at 1.00 ATM. And then what I can do with this guy here is I can do the exact same thing for if it was at 0.897, right? So again, moles here equals C times V. So moles is, again, 2.4488 times 10 to the negative 4. This was moles per liter times, I have a constant volume, right, of 4.90. So my moles here would equal, I have 2.4488 times 10 to the negative 4 times 4.90, which will give me 1.199. So 1.1, actually again, I'm going to round it to do that's 2 decimals. So 1.20 times 10 to the negative 3 moles. And then what I can do now is I have these 2 moles here. This is one is at 1.0 ATM, and one is going to be at 0.897. So what I can do is I can find the difference between these 2 moles, right? So I can subtract both of these numbers here, and that's what they're going to do with the moles here, right? So I'm going to subtract these 2 guys here, and you're going to get, let's see, 1.34. Let me subtract these numbers for you. 1.34 times 10 to the negative 3 minus 1.2 times 10 to the negative 3. So you are going to get 1.608 times 10 to the negative 6 here, which is slightly odd here. So let me just check their math here. Since moles is volume times molar solubility, they just put negative, oh no, 4.90 here is the That's good. That's good. Minus 4.90 times 2. Yes, times 2.44 here. So that's fine. So this math is good here. I don't know how they got this number here. Let me just recheck my math. So I'm gonna get, again, I have 1.34 times 10 to the negative 3 minus 1.20 times 10 to the negative 3. Yeah, I have 1.4. Sorry, yeah. So my value here, the difference here, I think I inputted something wrong in my calculator here. But basically, I'm doing the moles of, so let me write down the moles here. The moles of O2 that are being released equals basically the moles at 1.00 ATM minus the moles at 0.897 ATM, right? This here would be 1.34 times 10 to the negative 3 moles minus I believe it was 1.20 here, times 10 to the negative 3 moles. And then this would give me, this value here is 1.4, right? This here is 1.4 times 10 to the negative 4 moles here. And once we have our moles of O2, we can simply just convert this into mass, right? Because we want the how much oxygen here. So I'm going to convert this into mass here by saying, and I know that moles here equals mass over molar mass. So therefore my mass here is simply just moles times our molar mass, right? So mass here equals our moles, which is 1.4 times 10 to the negative 4 moles, times our molar mass of oxygen. Remember, oxygen here is O2. It's a diatomic molecule, so O2 is simply just 15.99 times 2 here. I'm going to round to 16 for the sake of, for quality of life. 16 times 2 is 32 grams per mole. So finally, moles cancel out, and I get grams, right? So I have, again, 1.4 times 10 to the negative 4 times 32 would get me, my value here is I have 4.48 times 10 to the negative 3 grams here. And this here is how much oxygen will be released from 4.90 liters of water in an unsealed container. And as you can see, this here is it's almost the correct answer. Again, it's probably some rounding errors, but it's the same magnitude and it's almost the same number here. So the solution here is correct. They probably carried more decimal places than I did. Grade analysis here as well. So yeah, they probably carried more decimal places, hence why it's like my number is slightly off. But the work here is great. So that was a 3-part question. Sorry about that. And that was number 4. Number 5 is asking which are Lewis acids and which are Lewis bases. So Lewis acids, acids versus bases. So again, I have 5 compounds here. So I have CO3 plus, I have BCl3, OF2, Cl minus, and CO2. So it's asking what are Lewis acids and what are Lewis bases, and which one are they, right? So I like this solution here because it's giving us a definition, right? So it says Lewis acid here is any species that can accept a pair of electrons. So again, if you think of an acid, it's accepting electrons, right? So in this case, if you recall from Bronsted-Lowry theory, we're accepting a hydrogen. A Lewis acid is much more broad, as we're saying that it's accepting a pair of electrons here. So basically, a Lewis, or I'm going to say La, or for Lewis acids here, can accept pair of electrons in E minus. So therefore, a Lewis base here obviously is going to, it's going to donate, right? It says Lewis acid can accept a pair of electrons and all cations, and then Lewis base can donate here. That's good. So it can donate pair of electrons here, right? So now we have to look at our chemical formulas here. We're asking, okay, what can accept electrons and what can donate electrons here? So let's look at CO2 or CO3 plus, right? That's the first one here. There we go. CO3, 3 plus here. And this here, I have CO3 plus here. This here, again, if I drew the Lewis structure for this guy here, I would get something like this. I would get basically this carbon here, bonded oxygen, bond oxygen, bond oxygen. And again, these two guys here and have a charge of 3 plus, right? So it could probably, one of these guys would make a double bond here, and then I would get lone pairs here, lone pairs here, lone pairs here, and a lone pair here, right? So again, this here, again, isn't very, very stable, because if you look at our carbon here, it has a lone pair, right? It has a positive charge here. It wants to accept a pair of electrons here, right? So this here, it wants to accept probably like an electron from hydrogen or something like that, or something else to basically help or not accept, but it's going to basically, it's going to accept a pair of electrons here so that it can rearrange its shape, right? So again, here it says CO2, after cleaving one pi bond from CO2, there's a negative charge over the carbon atom, which makes it a Lewis acid, right? So again, if I were to deprotonate, or deprotonate in the sense that I were to basically remove one of these pairs of electrons here, it's going to be ready to accept a pair of electrons here. So CO3 here, CO3 positive is a good Lewis acid, and same with and they wrote here BCl3, right? So boron trichloride here, and so here boron trichloride looks something like this. And again, I have a lone pair on boron here, right? A lone pair on boron here. Again, boron, we can say it can make 3 bonds here, but it can also hybridize to make more than 3 bonds. Right? Because boron very readily accepts electrons from other molecules, which generally behaves as a Lewis acid, right? I could actually get BCl4 here, and if I could actually accept another pair of electrons here on chlorine and make maybe BCl4, that would make it a tetrahedral shape, right? So boron's actually very, very good because it can accept, it's always a good Lewis acid because it can always accept pairs of electrons. So BCl3 are both Lewis acids. So Lewis acids. Let's go to OF here. OF2 here. OF2 here. So let's look at OF2. Again, if I'm looking at the Lewis structure here, I have O, bond F here, and then I have again a lone pair on here and a lone pair here, right? So in this case, Lewis bases, they can always donate a pair of electron to an electron acceptor, right? So again, you can donate to BCl3, for example, and make a bond, right? So for example here, OF2 has 2 pairs of electrons it can share with, right? I have 1 pair here and 1 pair here. I can donate these electrons to another species to create a base here. So this here, OF2 here, is a great Lewis base. And same with Cl- and CO2, right? So CO2 is actually CO2 is actually an acid here, but let me look at Cl- here first. Again, Cl-, again, if you look at the structure here, 1, 2, 3, 4, 5, 6, and then 7, 8. I have 8 electrons here. Very, very easy for me to donate a pair of electrons here. I have 4 pairs of lone pairs of electrons. I can always donate a pair of electrons here to get to, for example, hydrogen here. I could donate this to make HCl, right? So again, chlorine minus is a good conjugate base of HCl, which means therefore it's a Lewis base, right? So that's great. And then finally, I have CO2, right? So CO2 here. So CO2, if I look at the structure here, again, I have lone pairs on carbon here. I have 2 lone pairs on carbon here, and these I can obviously donate these electrons to somebody else for me to create a base, right? So it's actually very, very cool. You have CO3 plus, and CO2 here, and CO3 plus behaves as a Lewis acid. This here is a Lewis base. You can think of this as conjugate acid and base pairs, right? You can think of these two as conjugate acid. This acid here, I know CO3 plus is my acid. The conjugate base of that, if I were to depronate it, I would get a conjugate base here, which is a Lewis base here. So Lewis acid here and a Lewis base. So again, the same thing. You can think of this concept as conjugate acid and conjugate base. However, we're extending it to Lewis acids and Lewis bases, where we're expanding the definition as to accept or donate electrons. So this here solution is correct. Good analysis. This is number 5. Number 6 is asking biphenyl C12H10 is a non-volatile, non-ionizing solute that is soluble in benzene at 25, I want to say that's degrees Celsius. The vapor pressure of pure benzene is 100.84 torr. What is the vapor pressure of a solution from dissolving 15.4 grams of biphenyl in 29.7 grams of benzene? Okay, so we have, this is a long question again. So let me look at, so what is question 6, right? So let's see. So these are all basically university level questions at this point. But you probably would not be asked any of these guys in probably in a secondary level setting. It's more so in a university level setting for most of these problems here. So biphenyl is, again, I have C12H10, right? So let me write this down, C12, or I've given the mass of both of these guys. So let me just write down the mass of C12H10 is equal to 15.4 grams, and the mass of benzene, which is C6H6, equals 29.7 grams. I'm given at 25 degrees, so at 25 degrees Celsius, the vapor pressure, or at 25 degrees Celsius, the vapor pressure, so I can say P here, of pure benzene, so C6H6 here, would equal 100.84 torr. And it's asking us what is the vapor pressure of a solution if we dissolved both of these guys here. Okay, so in order for us to figure this out, what we have to figure out first is our moles, right? We have to figure out our moles here because we care about the mole fraction, and we can relate moles to our partial pressures as well, and that's why we can't really work in grams here. So in order for us to convert from mass to moles, we're obviously going to divide by molar mass. I know that moles equals mass over molar mass, right? Moles equals mass over molar mass, and therefore, because I have mass here, I want to find moles here, so I'm going to simply just divide by our molar mass. I'm going to divide by the molar mass of this and the molar mass of this. So molar mass of C12H10 would be basically 12 carbons times the molar mass of carbon, which is 12, plus I have 10 hydrogens. I'm going to multiply that by 1 gram per mole here. And this is all done here. Same with C6H6. Again, I have 6 carbons here, and I'm going to have 6 hydrogens here. So I'm just simply finding the molar mass, and I'm going to divide both of these guys. So, and then let me type this into my calculator. I have 15.4, I'm going to divide by basically 144, which is 12 times 12, plus 10, right? And this will give me a value of 0.1 moles of this is C12H10. And then for this guy here, I have 29.7 here. I'm going to divide that by 12 times 6 is 72, plus 6 here would give me 0.38, which is vastly different from what they're doing here. So I don't know what's up. It might be a rounding issue. Yeah, it might be a rounding issue here. So let me instead of doing 12 and 10 here, let me just I'm going to do the exact molar masses, so I avoid a rounding error here. So I'm going to do 12 times basically 12.011 here instead of 12, just to avoid some type of decimal error here. So 12.001 grams per mole, and this here was 10, right? So 10 times 1.001, I believe, is hydrogen, or 1.008, sorry, 8 grams per mole. Just to avoid some type of confusion here. Again, this is 12.01 grams per mole, and this here is 1.008 grams per mole here. And then let me do that on my calculator here. And I would get, let's see, so 12 times 12.01 plus 10 times 1.008 would give me a value of, the molar mass is 154.2. If we divide that by 15.4, I would get 0.99 here. So something is up. Oh, I understand why now. they messed up here. So they wrote 17.9 instead of 15.4, and they wrote 27.4 instead of 29.7. So I think they messed up their numbers here. So I guess their solution will be incorrect. So let's just actually solve for this solution here. So this here is going to give me 0.09987 moles. And then let's correct this solution. So 12.01 plus 6 times 1.008 would give me a molar mass of benzene is 78.108. I'm going to divide that by 29.7 here. And this will give me 0.33824 moles of benzene. So now these moles of benzene, so I can figure out the total moles here. If I add both of these guys together here, I'm going to get answer plus 0.09987. My total moles here is 0.48, right? So again, basically different from this value here, slightly different because they wrote they inputted the wrong numbers into our calculation. So this here is our MT, right? Our total moles here. And what we care about is benzene, right? We care about specifically benzene because we already have the partial pressures of only benzene. We don't have the partial vapor pressure for we don't have the vapor pressure for biphenyl here. So what we're going to do is we're going to find the mole fraction of specifically benzene, right? So I'm going to simply just divide moles of benzene by the total amount of moles. So 0.38 divided by 0.48 here. So I'm going to get the mole fraction. I'm doing MF of C6H6 is going to be basically equal to 0.38024 moles divided by basically 0.482011 moles. And this here that's the total mass here, total moles here. This would give me a value of 0.79120. I'm going to do 2 decimal places here. 20 here. And this is the mole fraction here. So once we have our mole fraction, again, what we can solve for is our partial pressure, right? Because we know here our pressure here is our at 25 degrees is 100.84 torr. I can simply find the partial pressure now, right? So I can say that partial pressure, or my pressure here, my vapor pressure here, so P V of C6H6 is going to equal the mole fraction, or X here, of C6H6 times our partial pressure of C6H6, right? So this here would equal, I know it's 100.84 torr. This here, our mole fraction here is 0.729, right? 7290 times our partial pressure of C6H6. I mean, 7290, right? Yeah, 7920, sorry. 7920. And then I can basically divide both sides by that, and I would get my partial pressure of C6H6, or benzene. Why did I write H first? Sorry. Would be 100.84 torr divided by 0.7920. So partial pressures of basically C6H6 would be 127.32 torr here. So as you can see, this guy here, they did. Oh, sorry. This is the wait. This here is the PO here. Oh, so this is a total pressure. Sorry. So this here is the total pressure. So sorry, I messed up my equation. I subbed in the wrong P here. My bad. So I have this is the total pressure here. Total pressure here, and I'm already given the partial pressure. Sorry. So I'm looking for the total pressure here, which is 100.84 torr here, and I can basically set torr here equals pressure here equals 0.7920 times 100.84 here. So the solution is 79.865 torr, or you can basically round it to 79.87 torr here. So I'm going to say here solution is incorrect because they messed up the first kind of part. The correct answer 79.87 torr, and then basically the reason why is that they messed up this part here. So I'm going to copy and paste it. It was supposed to be 15.4 here. 15.4 here, and then it's still resolved in 29.7. Solved in 29.7. So I don't know if I can bold this. Nope, I can't bold this. So this here would equal drastically different moles here. So this, I can copy my answer here. My answer was 0.09987, and this guy here was 0.38024 moles. Therefore, it changes our answer to changes our answer. So I'm gonna say solution here is incorrect. And then finally, I guess I'll just do this last question here. This one would be number 7 for today. And we'll save the rest of the problems for next time. But it's asking rank the given compounds based on their relative acidity. So let me go from, I guess I'll go from strongest to weakest, just like the solution did. So I have H3C, so H3CC. And then I have CH. I don't know if it's a formatting issue. We have CHHF. I don't know if this is one compound here. This is kind of confusing. I think it doesn't. So, oh, I have C triple bond H. That makes more sense here. I think they forgot the spaces. So this here is C. C here, H3C. So this is, so let me give me a second. So this is H3C, CCH. So this is a methyl group, and this is my triple bond, and this here is the H. Let me just draw it out actually. So I have a triple bond. I have 3 carbons here. So this here and then this here would be H. Yes. So this here is H. Yeah, it's simply just this actually. Yeah. So that's gonna be. So that's the first one. This is just a formatting issue. That's screwing me up here. And then I have HF. And then NH3. And then H2C. So this is H2C double bond CH3 and then CH4, right? Okay. So let me draw this out here. So I have a double bond here, and then it's bonded to 1, 2, and then it's bonded to a methyl group here. So that's this guy here. I can erase this, and then I have these guys here. Okay, so I have basically these 5 compounds here. So 1, 2. So let me draw this in blue. So this is 1, 2, 3, 4, and 5. It's asking us, okay, so it's asking us which is the strongest acid. So obviously strongest acid is HF, right? Ionic compound, hydrofluoric acid here, very, very strong acid here. So strongest, number 1 here is good. So I'm going to say that this here is my strongest acid. I'll put this as number 1. Next here is I'm looking at what is my next strongest acid. So I have an alkyne, and then an alkene, and then NH3, and then CH4. So if you look at our compounds here, if you look at it depends on the relative acidity, right? So again, NH3 here, it basically behaves as a weak base, right? We know ammonia the KB of ammonia here is 1.8 times 10 to the negative 5, right? So again, it's a weak base. So it's actually not a very, very strong acid. So you can think of this as as a weak base here. So again, this is my strongest acid. I know ammonia here is my weak base here, and I'm gonna put the Kb value for you, just so you know. Kb here equals, and actually let me solve for the Ka for you. So Kb here, just give you some values, are 1.8 times 10 to the negative 5. So for my Ka of ammonia, I'm gonna do 1.0 times 10 to the negative 14 divided by our Kb value here to get our Ka. Relatively, this here is 5.5 times 10 to the, sorry, give me a second. I think times 10 to the 18. To the 18. Oh, wait, no, it's not. It's to the 8 here. Sorry, so give me a second. Negative 14 divided by, I think I input a positive 14 by accident. This is negative 5. Yeah, so it's 5.5 times 10 to the negative 5. Or times 10 to the negative 10 here. So as you can see, the Ka is pretty small. And then you have, again, Kas of our alkyne, and then our alkene, and then this here is our alkane or methane here, right? So you can probably figure out that methane here is our weakest acid. It's basically our number 5 here. And the reason why methane's our weakest acid is because it can't really, it's not going to accept more electrons here. Like if you look at the structure of methane, how is it going to accept more electrons? It's already saturated, right? So this here is definitely my weakest acid here. So this is not very good. So methane here is my weakest acid. Then it would probably, I would probably think that my alkene is going to be my next weakest acid. And the reason why I put my alkene next is if you think about the Ka value of basically an alkene, you can think of the acid. It basically acts as a Lewis, a slightly Lewis acid here, and the reason why is that it can actually accept electrons, right? The alkenes here, the double bond here is electron rich, so it's going to basically I'm always going to be able to accept electrons here. So alkenes are pretty acidic. Alkenes are slightly acidic, but alkynes are even more acidic, right? They have 3 bonds here, right? So I'm gonna say that my alkyne here will be taking our number 2 spot because it can accept basically twice the amount of electrons than alkenes can here. So depending on that, and again, what you can do is you can actually look at there's a pKa chart here. Let me just bring that up for you here. And this here helps you with the relative alkene, the relative acidity or the pKa's of your organic compounds, right? And as you can see here, alkanes are all the way at the bottom here. Again, they're negative 50 here, right? Or sorry, not negative, but around 50 here, around 50. Right? Whereas hydrofluoric acid here is basically negative something. So again, very strong acid. Alkanes are going to be the weakest acid, and then it's going to be our alkenes, right? Alkenes are coming up next here. So alkenes here would be number 4, which makes ammonia number 5, right? Ammonia here, again, you can think of this as an amine, or you can think of this as, I can basically switch this value. I can switch this Ka value into a pKa value, right? I can take the negative log of this number here, and let me just show you the number here. What I'm going to get, here, a pKa here is about 9.226 here, right? So again, if you look at our chart here, 9.26 is about the protonated amines here, and this here is going to be pretty it's going to be more acidic here, and alkynes are actually going to be even less acidic than that here. So I can think of this as, this here will not take our number 2 spot, so number 2 spot is going to go towards our ammonia, and then 3 will be alkyne, and then alkane, and then our methane, right? So again, if you look at this chart here, the most acidic here obviously is hydroiodic acid, hydrobromic acid, hydrochloric acid here. And as we go down the pKa, as we increase our pKa's, it's going to be least acidic, right? So as you can see, HF is obviously number 1. Number 2 would be ammonia, right? A 2 would be ammonia, which would be the protonated amines here. So NH3 here would be about would be our pKa's. and then let's see, and then so get 9.26 here. 3 would be our alkyne, right? Alkynes exist kind of here at pK 25, and then it'll be our alkene, and then our alkane here. So this is 1, 2, 3, 4, and 5. So they got it a bit mixed up here. They're missing NH3 should be number 2 here. So I'm going to say solution is incorrect. The correct order is strongest acid here would be HF, and then it'd be NH3, and then our alkyne, alkene, and then alkane here. So this solution here is incorrect. So again, thank you so much for watching the stream here. Again, my name is Joey. I stream basically from Monday to Friday. Monday, Wednesdays, and Fridays are my chemistry stream. Sorry, my math stream, my bad. And Tuesdays and Thursdays are my chemistry stream. So you can stay tuned for that. So again, thank you so much for tuning in. Again, stay healthy, stay safe, and have a great day. Take care.